to all the panelists who are with us today and joined this panel alongside myself, and also thanks to all the participants that are with us today throughout the panel. Special thanks to you again, Daniel, for organizing this interesting event and giving us a platform to spread the message among the community. So my name is Mostafa Farrokhabadi. I'm the Senior Director of Technology at BluWave-ai in Ottawa, Ontario, Canada. And the topic of our panel for today, broadly speaking, is the role of artificial intelligence in grid-connected microgrids. We have, apart from myself, we have three panelists today. Cameron Sutherland from Greencat Renewables in UK, Ehsan Nasr from Microsoft in United States, and Ashkan Rahimikian from I-EMS in Canada. So without any further delay, I would like to start the panel for today. I guess the first presentation would be by myself, which actually I'm gonna go ahead and share the screen, and after that we'll go to Cameron, Ehsan, and Ashkan. So I'll share my screen in a moment if you just be patient a little bit. Okay, let me see here. Okay, great. So I guess everyone is seeing my title slide, AI in Grid Connected Microgrids, BluWave-ai. Can someone sign me that you're seeing this or confirm by audio, please?
Yes, looks great. Thanks.
Thanks, Daniel. And I see Cameron also nudging the head. Okay, great. So basically, I'll start with discussing a little bit of the disrupting trends that is happening in our power systems as we know it for almost a century, and what's the role of microgrids in this whole story, and afterwards artificial intelligence. So the first disrupting trend to power energy systems is the decarbonization initiatives. It's being driven by climate change mitigation policies and the overall attempt on the planet to flip the share of renewable energies from 15% penetration today to 85% penetration by 2050, regardless of the increase in the demand, which I'm gonna talk a little bit in the next disrupting trends. The impact of decarbonization obviously is introduction of intermittent and stochastic renewable energies, which would introduce generation uncertainty in the system, and following that would be probably some grid stability problems because of the uncertainty of operation and volatility on the electricity market. We have the digitalization trend, which is a result of the proliferation of advanced metering infrastructure, connected devices, and the fact that a smart grid is actually appearing on the intersection of information communication technology and power systems. And the impact is it's a threat in a sense that it's disrupting the conventional operation and control and monitoring centers, but it also opened doors for opportunities of big data applications. Decentralization is another trend, which is the result of obviously increased penetration of distributed energy resources, the fact that these resources are becoming cheaper and cheaper every day, and also the call for higher reliability in the system, the absence of the single point of failure, so on and so forth. Impacts would be the rise of prosumers, the so-called prosumers in the system, producers and consumers of energy at the same time, which would add to the control complexity in the system, and obviously would also provide the opportunity of additional flexibility obtained from the distributed energy resources. And finally, we do have the electrification, We have the growing demand in developing countries, and we have the transportation electrification in developed countries, which actually is on its path to increase our total global demand from around 15 terawatt today to around about 125 terawatt by 2050. And that would, the introduction of EVs, electric vehicles, electric fleets would add to further decentralization in the system. Severe demand peak because of the transportation electrification is expected to be a consequence, and higher uncertainties also is another byproduct of electrification, in particular in the transportation sections. So this disrupting trends is adding to the initiatives to decrease the cost of distributed energy resources. We had 77% drop in PV levelized cost of energy since 2009, 38% drop in wind levelized cost of energy since the same time. We are expecting a significant drop in the cost of lithium-ion batteries by 2030. The fact that the behind-the-meter energy storage systems are rapidly penetrating the system, we are expecting 40% of penetration by 2050, and 55% share of electric vehicles, global share of passenger electric vehicles by 2030 is projected, and finally 50% share of global energy coming only from PV and wind, obviously on top of other renewables that would add to around about 85%, including hydropower. So in this context, microgrids are going to be a key enabler in the system. So what you see on the screen is a typical outline or schematic of a microgrid. It's a cluster of distributed energy resources and demand that actually act as a single controllable entity with respect to the upper level system, transmission level system. And theoretically, it should be able to transition from grid connected mode to islanded mode without interruption of energy. So it exists in multiple forms. It exists in isolated forms in remote communities. It exists in enterprise institution formats in developed countries, modern distribution level systems, so on and so forth. And usually it has multiple control hierarchies. I'm not going to go through details of each one of these control hierarchies, but the fact that microgrids would provide a feasible solution to mitigate the control complexity as a result of distributed energy resources, provides flexibility opportunities to operate the system and obtain the most out of the operation of these resources, make microgrids a key enabler of decentralized, modern, smart grids. So in this context, BluWave-ai, one of the key focuses of BluWave-ai is active distribution systems and microgrids operation. We are a company founded in 2017, and we are on path to become one of the top premier clean tech startups. We have so far raised over $5 million between pre-seed and seed rounds, including provincial and government grants. Our prototype products include the first ever, we claim the first AI-enabled dispatch in a Canadian utility. No one so far has disputed our claim, so I think we are good to go with that claim. And also our prototype products, which is in operation for Indian utilities and markets. We have 1 USPTO granted and 5 non-provisional USPTO active applications. We are present on 3 continents in between our customers, partners, and we have long-term software as a service contracts already in place. We have received so far an array of awards, including the finalist for the Startup Energy Transition Award by German Energy Agency, the winner of World Energy Council in Abu Dhabi, the Smart Grid category winner of the World Energy Council last year, 2019, and the recipient of the Clean Tech Company of the Year from the IEEE Ottawa section. The 3 continents presence includes Canada with Hydro Ottawa, IESO, Tuglig Energies, Summerside Electric, UK with Greencat Renewables, India with Tata Power, and United States with an array of partners including Microsoft and IBM. Our product architecture. So we do have on one side the utility scale transmission level power plants, renewable energy generation farms, so on and so forth. On the distribution level, we have the three sectors of local energy resources, electricity consumers, residential, commercial, industrial, and EV and fleet operators. And we have one module, the so-called BluWave-ai center module, which hosts our computationally intensive part of the product in the cloud, currently in Microsoft Azure. And we have the BluWave-ai Edge module that either physically or logically resides on the customer premise, interfaces with the essentially control and monitoring centers of the customer, and also we communicate with the energy trading centers on the system operation level and system operators. With that, we basically our goal is to enable the transition to smart grids. Obviously, microgrids are a key component by providing a holistic end-to-end solution that combines predictive analytics, data-driven adaptive optimizers, and distributed energy IoT platform. The end result for our customers would be essentially the decrease, the actually increase in operational efficiency, such as a better rate of supplied cost of energy, less emissions, so on and so forth, with minimum capex, right? So we can squeeze the most out of the available capex for customers' projects to essentially optimize the system operation. And optimization, obviously, in our field means lower cost of supplied energy, higher reliability, stability margins, as well as lower emissions in the system. So I'm going to go through one example of what our product is about, and what are the features and how microgrids tie itself into the story. So we have an ongoing project for the University of Ottawa microgrid. This is a campus microgrid type with a considerable size of energy storage, 5 megawatt of power, 20 megawatt hour of capacity of energy storage. The campus load peak is around 11 megawatt, happening throughout the peak of the academic year, and the average consumption is around about 8 megawatt. And there's a small PV farm on site as well, which is right now at the moment is generating a rated capacity power of 20 kilowatt on the AC side, but is expected to increase as we operate. So we had an ongoing project with the University of Ottawa on the energy arbitrage objective. Energy arbitrage, for those I believe most of the participants probably are already familiar with the concept, but for those who don't know, energy arbitrage is the task of displacing the energy consumption from more expensive periods of operation to cheaper periods of operation. That's essentially is defined as energy arbitrage, and usually for microgrids it's done with the assistance of an energy storage system that is able to perform that energy displacement in the system. So this is a top-level architecture of how a data-driven optimizer looks like. We are, again, our approach toward such kind of problems is usually an ensemble hybrid approach between the conventional linear programming techniques and data-driven optimizers. But what you see here is a purely data-driven optimizer. So basically what happens is this entire optimizer, which you see here, can be counted as one agent that interacts during offline training period with this microgrid model, the model of this microgrid, and learns the optimal policy, the optimal actions for that microgrid through a set of interactions. So you could think of the microgrid at any moment having a state of operation as S, which is essentially, let's say, the state of charge of the battery, the electricity price, the demand at the system. Then the agent takes an action A and arrives at a new state S prime, an energy, basically with a cost function. So that cost function could be the cost of the electricity that it takes from going from state S to S prime through action A, the emissions that is as a result of the action, whatever is the objective function. In this case, because we are doing energy arbitrage, obviously the objective function is the cost of energy obtained from the upper grid, right? So we take these samples, we train the model. So training essentially is the process of the model gathering all these samples, analyzing these samples, and inferring an optimal policy that ties a set of actions to each state, right? So then the optimizer learns what actions are the optimal actions in any state of the system, in any situation with a particular state of charge, particular PV generation, particular load consumption, particular electricity price. What is that optimal action that can be taken with respect to that state? So this is called the offline training. So offline training is essentially gathering these samples, analyzing these samples by the data-driven optimizer, and arriving at an optimal policy. The conventional way of doing this is obviously through linear programming techniques that try to predict the future state of the system and solve a complex mathematical problem that arrives at the optimal actions for the system. There are a variety of drawbacks with that approach that doesn't exist in this approach, and a few drawbacks with this approach that doesn't exist in the other. We can further discuss after in the Q&A session if there are interested folks. But at the end of the day, each one presents their own benefits, and a hybrid approach might be the best approach forward. What I'm going to present today is though the purely results of comparison of this approach versus conventional programming techniques. The problem setting, what you see here is the electricity price. The red line is essentially the moving average of that electricity price, just to give you an idea of what electricity price paradigm the microgrid is operating in. And the experiment setting includes a training horizon of January 2018 to March 2018. So we are just dealing with a very short training horizon to highlight the competency of such data-driven techniques that only relies on 3 months of training period. The test period for some of the results I'm presenting is only 1 month, but for an entire results is 1 year of training, which is tabulated, and I'm going to discuss in next slide. And we compare the performance of the data-driven optimizer with a rule-based optimizer, essentially an optimizer that takes constant actions every day, that is predetermined by the operator, a random policy which takes random actions for the energy storage within the acceptable constraints, randomly charging and discharging the energy storage, and a conventional linear programming algorithm. So just to give you an idea, these pictures are presenting the actions taken by each algorithm. So this is the random algorithm. Obviously the blue and red lines are the electricity price. The green dots are the actions taken by the energy storage, right? So in these random actions, the actions are spread all over the typical sample period we are showing here from April 9 to April 12, 2018. And you could see that obviously, as you expect from a random policy, the actions are scattered all over the system. The rule-based, again, is a predetermined actions taken by the energy storage, and this is basically the rule-based policy determined by the operator. And then we do have the BluWave-ai data-driven optimizer, that the actions, as you see, is not as scattered as a random policy. It follows a particular pattern of charging at a particular part of the day and discharging at another part of the day, but it's not exactly as a rule base that is just a block of charging, a block of discharging, and a block of inactive operation. So in terms of what happens for income comparison, we actually tested the models once with considering the battery degradation. So what is the impact of the policy, the optimizers on the battery lifetime, and once without considering the battery degradation, just to see what is the theoretical possibility. So I'll go through each one of these just to give you an idea again what each one is. BluWave-ai is the data-driven optimizer developed by BluWave-ai. The model-based with forecast is a conventional linear programming optimizer that ingests forecast from the system, like the forecast of the price, forecast of the demand, forecast of the renewable energy, so on and so forth. Rule-based system obviously is predetermined set of actions defined by the operator. Random is just taking random charging, discharging actions just to provide a benchmark sake of comparison. And model-based Oracle is essentially the theoretical bound of how much you can obtain, how much revenue you can obtain from the system. That theoretical bound is established by providing a programming optimization technique that ingests perfect forecast from the future. So we feed this programming technique with perfect view of what's going on with electricity price in the future, what's going on with the demand, what's going on with the renewables. So the model ingests perfect forecast, and as a result provides you a theoretical bound of what could have been achieved, what revenue could have been obtained if we had a perfect knowledge of the future and an infinite amount of time to calculate the perfect optimal actions with respect to that perfect knowledge of the future, right? So what you see here is, let's first focus on this part of the table. The net income per year on the perfect policy would be $252,000 per year from the energy arbitrage. The second in rank is BluWave-ai, is 122K obtained from BluWave-ai data-driven optimizer. Then the model-based forecast is 33K. The rule-based is coming last in between the reasonable approaches with 42K, and the random policy actually loses money, which is not a surprise because it's a random policy, and you are not expect the savings or the loss of money to be very far away from $0, right? So on the degradation part, obviously the rule-based and random policy, you wouldn't see any numbers because those policies are fixed. There's no way that you would consider and change those policies to consider for the battery degradation. But you could see that the model based with forecast would here I want to add another point is that the charging discharging actions taken by each one of these methods, BluWave-ai, model-based with forecast and model-based with Oracle, once they are operating in the degradation paradigm, results in equal battery degradation per year. So we are looking at operations within these three models with equal battery degradation, right? And with that equal battery degradation, BluWave-ai saving was 61K. The perfect theoretical bound could have been obtained was 120K, and the model based with forecast was actually severely suffering, was not able to solve for the battery degradation constraints, right? Because of the non-linearity of those constraints injected into the problem, and the savings severely was affected to only 2,000K per year. And that's one of the potential benefit of a data-driven optimizer and artificial intelligence optimizing the system is non-linearities can be dealt with much more efficiency as compared to programming techniques. Another interesting point that I want to highlight before wrapping up my presentation is the computation time. So for the model-based conventional programming optimizer, we are optimizing for hourly intervals, and for each hour it could take anywhere from 4 seconds to 300 seconds, right, depending on the setup of the system, the state of the system. So it's anywhere from 4 seconds to 5 minutes of computation time for a conventional optimizer, versus for BluWave-ai optimizer, once trained offline, the inference is almost instantaneous, right? So the inference of the model, because there's not really any complex optimization being solved. It's just a model that intelligently inferred the policy and can take instantaneous actions once confronted with a certain state of the system. So the computational time of BluWave-ai is only a fraction of the second, and that also opens door to very high execution rate optimizers that are able to rapidly react to operation changes in the system. So assume that you have a high penetration of renewables that changing rapidly from a minute to minute, right? If you want to go with a model-based programming optimizer, you might not be able to update your optimization dispatches every minute because the problem itself takes 5 minutes to solve, right? Versus with a data-driven optimizer, you can actually run that optimization theoretically as fast as you can. The only concern here is probably you don't want to interfere with the primary control timeframes, so you can execute it, let's say, as fast as every minute, right? To also get a little bit decoupled from the primary control time frame of operation. So that brings an end to my presentation. I'm just going to go briefly talk a little bit for a minute onto what we believe is the impact of COVID on smart grids and microgrids. On decarbonization initiatives, actually COVID-19 is gonna help us to transfer the lesson we learned with respect to how we responded as a planet, as a species to COVID-19 systemic threat, and apply it to accelerate the climate change initiatives. On digitalization, we can use the virtual tools and techniques that are now prevalent and proliferated throughout the COVID to help accelerate the digitalization business of smart grids. Decentralization is likely to be decelerated in the short terms because of the investment issues and the market problems that we are experiencing, but no long-term impact is expected on the decentralization. And the electrification is actually, we see a good flow of venture capital money into high-tech areas, including electric vehicles that increase the system resiliency of operations. So high-tech resiliency is attracting investors, and that's a good news for people operating on the electric vehicle part of the story. So that basically means that BluWave-ai goal is to increase the operational efficiency of players, all the stakeholders in the smart grids, consumers, generators, system operators, utilities, distribution system operators, with reduced requirement for investment in the assets and reduced capex requirements, basically. So that brings an end into my presentation. I think we can open questions. We can leave the questions at the end to make sure that we have enough time for all the presenters, and we'll go through the round of QA probably just for the last 10 minutes of the panel. So I'm gonna actually stop sharing and then we can transfer to our next speaker, which is Cameron Sutherland. So I'm going to go through a brief bio of Cameron. Cameron is responsible for Greencat's wind, solar, and hydro due diligence work for a variety of funders and investors, and he provides technical oversight across the company's environmental assessment areas and asset management function. Cameron has an MSc in renewable energy systems technology and 14 years of experience in the renewable industry, mainly with onshore wind and solar projects of various scales across the UK and more recently Canada. His primary technical specialisms are in resource analysis and noise assessment, having produced more than 40 bankable wind assessments and carried out pre and post construction noise assessment at a number of sites. In his time at Greencat, he has managed more than 30 wind energy projects through the Scottish planning system and technically supported at all stages of wind, solar, and hydro project development from pre-planning to post-construction. So with that brief introduction, the floor is yours, Cameron, for sharing screen and going through your presentation. Thanks.
Thank you very much, Mostafa. I will just try and share the screen just now. Can everyone see the presentation?
Not yet.
Is that better?
Yeah, we see your screen, Cameron. Thanks.
Yes, so as Mostafa said, I'm also technical director in Greencat Renewables, and we're a specialist renewable energy consultancy based near Edinburgh. The company was established with the aim of driving down the costs associated with the development of renewable projects by offering a complete in-house consultancy and project management service. And Greencat has extended our operations to Alberta in Canada. And through that Canadian link, that was what got us started on working with BluWave-ai. And the particular project we're working with them on is the recycling, waste recycling facility in central Scotland. So this waste recycling facility had restricted grid access and was using diesel generators extensively for their consumption, and we had the opportunity to build out a 4-wind turbine project at the site. So I was just going to say a brief bit about the Microgrid project and describe that, give an indication of what the issues for control and optimization are at the site, how BluWave-ai, who we're partnering with, are helping us with that, and some further details on that and progress to date. So the project itself, as I say, it's quite an industrial site in Scotland. We have 4 wind turbines there in phase 1, which is now complete. And the 4 turbines, they are each 2.35 megawatt wind turbines. And the aim is at phase 2 that we put in a containerized battery unit of around about 2.6 megawatt hours. Phase 3 will be a solar farm, and at the moment it looks as if the solar farm may well overtake the battery in terms of deployment, or certainly some of the details that's going into the planning system very shortly. And then the other aspect of the project is we have these various on-site loads, industrial uses, some office space, and some domestic loads. It's not a classic microgrid in the sense that it's not very micro, but it is constrained to 7.05 megawatts. And by the time you add what is currently 9.4 megawatts of wind capacity with 6 megawatt peak of solar, and add a battery in there, and with the on-site demand, it is actually going to be operating as a microgrid with the ability to export surplus to the main grid. There may be opportunities to extend the export capacity in the future. So specific project issues that we have at the site. There was a high reliance on diesel generators on site. Those on-site loads are now connected to the electricity network on site now that the wind turbines are installed. There are increasing electricity costs for industrial consumers in the UK, and so there is the hope that this project will assist in stabilising those costs for the on-site users. There is an expectation that the on-site demand will expand in the future as they expand their waste recycling facility. They are trying to obtain further contracts for additional municipal waste to be handled at this particular site. And there is a desire from this industrial park to be sustainable. So they see this very much as a synergy between renewable generation and also waste reprocessing, and looking at the whole thing as a sort of 360-degree cycle of energy, if you like, from our waste going through the energy cycle. And of course, there is the obvious issue that the grid connection, the maximum grid connection capacity is less than the generation capacity. And this is likely to be the case into the future. General things in the UK that are driving this type of project, obviously there has been the increased penetration of renewables over the last 10 to 15 years. The UK is set for a very big expansion of offshore wind in particular, and we have a grid system that's designed for large generators that are not embedded in that system. And we are also seeing increased electricity price volatility. So, for example, in January 2020, this project actually saw quite significant negative electricity prices at certain times of the day when it was windy. There's also another element to it, which is the regulatory element. This project is, the grid connection that is there is part of the distribution system rather than the transmission system, and use of system charges and balancing charges have already increased at that scale and are set to increase further in the future. And of course, there's a driver for industrial users that not only are the electricity costs higher, but this particular industrial user was spending a lot of money on dirty diesel to power some of their factory units. We also have a situation in the UK where distribution network operators are moving to become distribution system operators. So that introduces new dynamics into the system. So what are the potential benefits of AI and the partnership with BluWave? Well, I've listed a number here, but the ability to optimize generation from multiple and variable sources, to optimize energy storage on site, to be able to use weather conditions and or market pricing signals to improve the prediction of what we will generate and what will be consumed on site, to potentially in the future look at peer-to-peer trading, which is not currently possible but is expected to become possible, and just better utilization of renewable energy. If we are going to more frequently in the UK encounter periods such as the January in 2020 where renewable energy is outstripping local supply, and then other periods where there's less renewables on the system but high demand from consumers. The other thing we want to try and do with the AI is to minimize our exposure to adverse balancing costs from the use of system, and try not to lose that too. So the proposed system inputs, and as I say, the wind turbines are in existence now, and they've been operating since January 2020. So we have a series of wind and solar generation. Eventually, we will have a battery that can be used to store excess, and we also have an significant on-site load, which can also take excess generation. We have the connection to Scottish Hydro in that area, and we will also consider the potential that in the future we may be supplying more than one external demand for electricity via peer-to-peer trading. and the AI has got to be able to take inputs from all these aspects and try and optimize the system so that we can minimize exposure to cost and optimize the value of these renewable assets. So the BluWave have been working with us this year, and they've been developing a model which takes climate data, demand data, production data, obviously real wind production data, and simulated solar data at the moment. They will be adding storage characteristics to that model, and they have also included price signals, and that will be used to develop a sense of when imbalances can occur in the system. And at this stage, we're trying to keep that model as flexible as we can, because we may, the situation with balancing charges in the UK is slightly unknown, and therefore we may have balancing charges in the future that are not currently part of the costs of the projects that we're running. Then once you've got a model, you can start to test it. So as I said, because the 4 wind turbines are up and because the grid is now constrained to 7.05 megawatts, then the model can now be trained against the live wind data, as well as using the simulated data for solar and so on. And so that process is ongoing just now. And the goals of that initial testing process is to make sure that the model can predict the generation and the on-state loads, can predict any overproduction to the grid and predict the conditions in which that's going to happen, and then prove any storage impact so that that will then feed back into the final sizing for the battery. And that will then end up going into a BluWave-ai edge optimized model, which will have the built generation, storage, loads, and the grid connection built in. And final output of the testing will be to look at the potential financial upside of the AI versus having a standard method of control, as Mostafa was outlining in his presentation. As I say, further testing phases may arise if we look at the peer-to-peer modeling and also incorporating ancillary services for battery storage. At this point in time, our primary focus is making sure we can use the battery as effectively for renewable energy on site, and that type of thing, and also minimizing exposure to high electricity costs. But there may be further ancillary services that we might be able to use a battery for in the future. So further possible development with this whole model is to look at minimizing balancing charges to external loads. And as I say, that's something where the regulatory environment is developing as we speak. Look at the possibility of the AI system becoming a first responder in the event of wide grid constraints. Allow the site to improve its response times and minimize the risk of renewables being the culprit for wider grid interruptions. So something that's happened this year in respect of COVID-19 situation is that for the first time, generators at this scale in the UK have been given the opportunity to bid into a mechanism of constraint payments, which were previously only existed in the transmission system. But because of the reduced demand during lockdown, even generators of this scale were sought to be able to switch off at particular times of peak demand. Now, at the moment, the way that system is working is very, very clunky, and the utility is kind of phoning up at 6 o'clock on a Friday night and asking if you're available to switch off at 11 p.m. In the future, I would expect that AI systems would be more widely used, and certainly AI would be the obvious candidate to be more widely used across the industry to actually bring those curtailments, if necessary, in automatically. And of course, as I'm hinting, with the development of this AI system with our partner BluWave, we would hope that this is a very repeatable model for the UK, given the changing regulatory environment. That's all I have to say. I hope that was not too whistle-stop, but gives you enough of an idea of how BluWave are helping us with this particular project. And thank you for your time. I'll take questions later, I guess.
Okay, thank you, Cameron, I appreciate it. So our next presenter is Ehsan Nasr. I'm gonna go through a brief introduction of Ehsan. He's a senior infrastructure engineer and program manager at the Datacenter Advanced Development Department in Microsoft US, leading several energy research projects. He received his PhD in electrical engineering from the University of Waterloo, Canada. Ehsan has worked in various electrical engineering positions. His current technical activities include renewable energy, microgrid, and advanced energy storage systems, artificial intelligence, and advanced technologies in data centers. He has worked at Canadian Solar from 2014 to 2018, leading various hybrid renewable energy solutions and microgrid projects such as Canadian Renewable Energy Laboratory, a unique testbed for microgrids in Canada. His work concentrated on power systems modeling, and design of hybrid systems, and is actively involved in several IEEE smart grid, microgrid, and electrical system standard development, IEEE working group and task forces, and is currently a member of IEEE Power System Dynamic Performance Committee and Technical Committee Program Chair of the PSDP. Ehsan has published several technical journal and conference papers. So with that introduction, the floor is yours, Ehsan.
Thank you very much, Mostafa, for the introduction. Let me share my screen. Just a moment.
Yeah, we see your system mode, Ehsan, not the actual presentation. So it's it comes in the, yeah, I think you have to share your other screen.
Okay, sure. Okay, so
yes,
can you see my
great.
screen? Okay, great.
Yep.
Thank you very much. Today, I'm going to talk about AI in grid interactive data center and the relationship between data center and the concept of the grid interactive features and the relationship of this to microgrid. I am a technical lead at Data Center Advanced Development and focusing on the energy storage and all the related technologies in data center. And for sure, AI is one of the top technologies that we are considering for the operation of the system. Okay, so as you know, here is basically the snapshot of the Microsoft cloud. And as you know, Microsoft designed and built and operate one of the largest cloud network in the world. As you can see here, we've got the over 220 data center all over the world, and we have more than 1 million of a fiber across a different area, and the 61 Azure network. Basically, that is a huge network of connection between different sites, and for this, every Microsoft product like Bing, Azure, IoT, AI, Office 365 runs on this infrastructure. Basically, we have infrastructure for all the cloud that we are providing to customer. But the interesting thing is that the growth is exponential. Every time that I need to talk in a conference, I have to go back and check and see, okay, how many Azure area that we've got, how many data center that we've got, and every time every couple of months, so we've got more and more data center and area and edge site that shows the exponential growth of the cloud industry. But the backbone of this cloud industry and the cloud is basically data center. Data center is, it shows one of the example of a data center that we've got in Dublin. And that is for every dot in the last slide that you can see, we've got the massive area, including a server and network device and generation, and to provide the infrastructure for the platform. And for every site, the data center is providing the base for that kind of a services that we have. But the question is that people they think about the data center is just the the racks of server, but in the reality is that is more than actual this server. We have a cooling system, we have a diesel generator as a backup, we have a battery for the UPSs, we have like a different stuff around the server, and that is way more than that. Because of the scale that we have the massive amount of like distributed generation asset in our fleet. And we are not only the basically IT hardware owner to provide the cloud services to the customer, but also we need to operate that DG or generation asset. And to operate this generation asset, there are some innovation around that, and we are actively look to see from the sustainability aspect, from the innovation aspect, how we can operate all of those assets efficiently. And that is one of the aspects of the operation of the data center. From the sustainability perspective, our approach is basically to invest and build the leading platform for the technology solution for environmental challenges. Basically, we are not only focusing on a carbon and CO2, but also we need to think about water, also ecosystem, how we going to get the land, and how the impact of like a build the data center in some certain area. And also we need to look at the waste, because the whole supply chain that we have and every component, every product that we are going to make, we need to think about the waste and full cycle of a system. And that is the 4 areas from the sustainability perspective that we are thinking to build the platform in order to enable and use the technology which tackle all of those 4 areas. And at the center of this is the employees. We are working with the customer, we are working with the partner from the software side, from the hardware side to achieve that sustainability goal that we have. And couple of months ago, we announced the sustainability goal to remove to move toward to the carbon-free data center in our fleet, and that is a big target for us, and would is kind of the starting point for the other industry and also cloud provider in this area. Just back to the sustainability, which can relate to the microgrid. We are talking about the data center and all the different aspects of a data center, but how about the energy? Energy actually is the big portion of our, like, kind of a big thing for us, because the consumption of the electricity that we have is a big portion of the total cost of the ownership for the building and operating the data center. And that's why if we look at from the sustainability aspect, we are buying more and more renewable energy from solar and wind in order to have close to the 100% of the renewable energy for our fleet. Just back to the scale that we have, we are not the power company, but because of the size that we have, it happened to us, we have one of the largest generation asset company, because we have all the diesel generator as a backup for our data center. Gigawatts of the power in our fleet we have in a different area, different countries, and we have to smartly optimize the operation of all those assets. This is, it shows we've got a certain goal from the penetration of the renewable energy, 60% 2019, and we set the goal to have 100% renewable energy by 2025. And that is one aspect of providing power to our energy area that we have in our fleet. But the question is that these buying more solar and PV is not directly connected to our data center, because it makes sense to buy a solar, to buy the power from solar and wind from the area that is a better place to have a solar and wind, and that is not exactly close to the data center. But we are just trying to see what our other innovation exists or opportunity in data center to use the asset that we have in a data center and providing some services back to the grid. And the idea is that from one side, we have challenges in the grid, and in the another side, we have innovation opportunities in data center. And with these two sides, we think we can build a grid-friendly data center, and it it comes, the data center can act actually as a microgrid and providing some services back to the grid, which I explained it in the next few slides. In a traditional way of data center, basically the conventional energy supply chain, we've got the energy from resources all the way to the transmission line, to the substation, and connected to the basically data center. And we have a distribution system inside of our data center to make sure we can meet all the availability requirement that we need at a server level. Because of that, we need to have some sort of a backup. If there is some outage in the system, we can provide the power to our data center. And there are different approaches to how to feed power to the grid. That is kind of the conventional approach, and the diesel or a battery in the UPS that we have is just providing the power to the data center. And so in the case of there is any outage to the system. But in a grid interactive option, we are thinking to kind of an active way to interacting with grid, and to monetize the existing and asset that we have in our data center. For example, the battery that we have in the UPS, or a diesel generator that we have, or any potential other technology that we may go to deploy in our data center, providing a different kind of a services to the grid, as Mostafa mentioned about the energy arbitrage. That is one of the example. But the next step for us is to how we can be a part of the grid, and the data center have an asset, kind of a dispatchable, providing power to the grid. And that is a kind of a concept that we have for a grid interactive data center. And we've done a couple of project and pilot around that. So in this concept, we are not going to only backing up our data center. And in this way, we're going to be smarter, cleaner, and more efficient on the operation of all the asset. And in general, that is not something that we are owning and operating all this stuff, all the generation asset that we have in our data center, and we are not working with the grid. Basically, we are integrating in one ecosystem, and that is the future of the technologies, especially in a data center industry. We've got, from a data center perspective, we've looked at a different side of the technologies to see how we can remove the carbon from our fleet. And from every aspect of hardware component that we have in our data center, and we looked at how we can efficiently operate, and to look at the different assets from a different angle. For example, we've got a bunch of different technologies that we looked at, like a fuel cell, grid interactive UPS battery, clean power backup, and also the liquid cooling. And in this presentation, I'm more focusing on a battery, just a quick overview of how we can use the battery inside of our data center to providing some services back to the grid. One of the example, just let me go back to the data slide. Just an example that we got on the battery system we typically have around for a few minutes battery duration in our data center in order to provide some backup services once the diesel generator is going to start up. And we thought that that is a good opportunity for us to look at and use that battery inside of our data center that we are typically have in any our data center, and use the new version of the battery can provide some services back to the grid. We looked at the different ancillary services back to the to the different areas, and every market they do have a different aspect from the business cases and also from the technical aspect. And one of the examples that we looked at is the frequency regulation at the PJM market. Basically, in the PJM market, we've got the signal called a RegB signal, and every 2 seconds we receive any DG owner which are going to participate to that market can receive a signal every 2 seconds. And the payment is basically how will that you can follow that signal. That is one of the example of the frequency regulation in this market. But the question is that how we can optimize the operation and how we can smartly to participate to this market. We started to look at just to participate to this market all the time, because we have, so in terms of the duration of the battery, we have a very short duration of the battery, and we have to be very smart on the battery degradation and the cycling of the battery. And one idea came to our mind is how we can use the AI to predict the payment from the system and combine it to the whole portfolio that we have, and to use the better prediction in order to participate to this market wisely. So we worked with our internal team to develop the model, and that is basically in the other side of the fence, we are providing the Azure ML and platform and the different services to the customer. And basically in our data center, we were one of the customer of our final product that we've got. And we worked with our internal team, and they came up with the model, and it shows there is a potential saving using ML versus the passive control system as the example in this particular application. And it shows that in this application, if we don't use the ML or MI prediction control in our system, we have to change our battery instead of 10 or 15 years, we have to change it every 1 year or 2 years. And basically it would add the cost and the capex to the system, and it doesn't make sense for us to move toward to that system without having that kind of a controller or AI. That is basically the whole concept of using AI in one of the examples that we have in our system. So I'm not going to go to the detail of this, but that is basically one of the examples that shows the AI can work and predict in a good way, basically, to provide more, to operate the system more efficiently. And my last slide is about the opportunities that we've got beyond data center. So I was talking more on a data center and how data center can act as a grid connected microgrid and providing the services back to the grid. Also, we do have the renewable energy as a source of the power to our data center, and the AI can act to operate all of those efficiently. But at the other side of the fence that we are providing a different services for the customer, for the startup that they like to develop their own AI platform or AI controller to optimize the system. And that is one of the, basically, it's just a kind of a closed loop that we are partnering with the customer and providing the platform for the customer that they can build their own controller and their own AI edge controller, and just providing all the services back to the grid and also to the different sector of the industry. And that is the beauty of the using AI that can impact all different industries, from the healthcare, from the industrial, and from all the different aspects on the other side of the industry that we're focusing. Thank you very much for your attention, and we're happy to answer any question that you have at the end of this.
Thank you, Ehsan. And I would like to add that I apologize. I think we are a little bit over time, but we extended the session for another half an hour, and I'm happy that we're still keeping all the participants. So apologies, Ashkan, as well. So last but not least, actually a very interesting presentation by Ashkan Rahimikian is going to happen next. Just briefly introducing Ashkan, he has 25 years of R&D consulting and software development experience in smart energy grids, power systems planning and operation and optimal control, and transactive energy markets by means of blockchain. He has served as a co-founder and CTO at AI2E, founder and CEO at I-EMS Group Ltd, and senior data scientist at Opus One Solutions, VP of engineering at GenSpace Inc. And Ashkan is a registered professional engineer in Ontario, Canada, and a senior member of IEEE. He has published over 150 peer-reviewed papers, is the main inventor of 2 US patents about smart grid software and software as a service. With that introduction, Ashkan, the floor is yours. Please go ahead.
Thank you very much, Mostafa, and all the participants for basically for your patience and listening to my presentation as well as the other fellows. So I'm going to share my screen with my presentation. I hope you can see it. And okay. So as Mostafa mentioned, I am the founder and the CEO of I-EMS Group in Toronto, Canada. We are part of IBM Venture Lab, and also co-founder and CTO at the AI, Artificial Intelligence to Energy company in New Jersey, USA, together with my partner, Andrew Peck, based in Pennsylvania. And today, basically the subject of my speech or talk is about EV fleet as a virtual power plant for vehicle-to-grid services to distribution system operators. And we want to see how we can utilize artificial intelligence optimization algorithms and a blockchain-based transactive energy platform to help the utilities of the future and also the community developers of the future, sustainable community developers and microgrid developers. So that's the topic of my talk. So what is the problem today that we are facing in transition towards smart grids and smart cities? distributed energy resource and EV fleet as virtual power plant integration and interoperability with the medium voltage, low voltage power distribution grids in evolving smart cities. This is one big challenge that the utilities and system electricity system operators are facing. So what is the solution that we propose? We are proposing to use 5G cloud with distributed AI and software as a service modules for monitoring, control, and energy trading between the distribution system operators and the prosumers of energy. So what we propose as basically the correct platform for SaaS, software as a service for the future grid operators and microgrid operators is such that, so in the first layer, the physical layer, we have the hardware and the IoT sensors and AMI systems, and we can collect all the data from controllable loads, DERs, energy storage systems, and so on, HVAC systems, so on and so forth. And then you can feed those data into the predictive analytics engine that uses data mining, machine learning, deep neural networks for network topology estimation, load forecasting, and DER output forecasting, such as PV and wind generator forecasting. Then we feed that knowledge into the optimization engine. If we are optimizing the grid, then we call that tool DERMS, DER management software. And if we are doing it for a sustainable smart building, commercial industrial building, then we call it BEMS, Building Energy Management System. What do we optimize for? The variables are this DER output and the flexible load schedules, which could be 5 minutes ahead or 1 hour ahead control, changing the set points. What is the DSO's objective in the grid? So it could be peak shaving, network loss minimization, and reliability maximization. What is the building energy manager or prosumer's objectives? So it could be energy cost minimization or the prosumer's profit maximization via the transactive energy platform that both the prosumer and the DSO are registered in, and they use that platform for basically trading energy. And the last layer of this software as a service in the cloud, it's the peer-to-peer transactive energy market with blockchain platform, both web and mobile applications and smart contracts and intelligent software agents and the bidding strategies and negotiations. So this is one good example that our US partner Luminex and I-EMS are working with target stores to basically equip them with both hardware and software of the future, meaning they can use DC microcells, 48-volt DC microcells to connect all those rooftop PVs, battery storage, EVSE or the charging stations, and basically other type of DC loads to the DC bus bar system. And then we use basically the LAN local area network, which could be Z-Wave or other types of inside the building sensor networking and connecting the sensors together and sending the data to the AI distributed 5G cloud. We are working with Sienna currently to use their intelligent cloud for our computations, including predictive analytics, optimization, and transactive energy platform. And as you can see in this picture, we have physical data flow, we have energy flow, and we have the trade data flow. And for each one, we have a different type of application. And then we have these target stores equipped with the microcell, with the software that can either, sometimes if they want to, they can minimize the cost of energy by optimizing the combination of solar generator, battery storage, and flexible loads, and also charging the EV cars, the customers and staff at target. And sometimes they can transact energy and make money from transactive energy either through the V2G, vehicle to grid energy and also selling the power from the solar and battery back to the grid using the platform that we have in the cloud. This is one example for one building. And then the other example could be solving this transactive energy market, clearing the transactive energy market for a medium voltage network. For example, C-grade medium voltage network that I can publicly share with you folks. So we have picked it. It has several PV, solar PV generators in it, CHP diesel, fuel cell, battery storage, and the flexible loads as demand response players. And for a typical day in 2019, we have basically predicted the load profile for this network for 24 hours and the solar PV profile for 24 hours. And what we have added to this network, because the C-grade didn't have that, and we wanted to show the value of EV fleet as a virtual power plant, and basically using vehicle to grid services when the system operator needs that power. We have added basically 6 EV chargers, 3 AC fast chargers, 3 DC fast chargers with the spec that you can see here: efficiency 95%, power factor 96%, and for one, the charging time is 3 hours, and for the DC one is 30 minutes. And we have conditions for the EVs. We have modeled 100 EV cars in this network to trade energy with the EVSEs, whether buying or selling. And there are some conditions. So a car can charge when the battery SOC is between 30 to 50%, and can discharge when the battery SOC is between 90 and 100%. We limit the cycle of charging for one EV for one charging, discharging, charging per day, because we know that the battery in the EV car is one of the most expensive assets in it, and the driver, the owner of that car, they want to use it and utilize it for as many years as possible. So we limit the charging, discharging, charging per day, only one cycle of charging and discharging and being ready for the next day. I also need to talk about the blockchain architecture that we are using that has several layers: the application, transaction, block, and the network. And we use different standards for security, cybersecurity. And we are using proof of authority for basically acknowledging and accepting the transactions. And so it's pretty fast. I can show you at the end the performance of the blockchain that we are using, and the consensus algorithm is proof of authority. So as you can see in this example, we have 3 players that are participants of the transactive energy platform, and each of them has an intelligent agent that is a learning agent from the market, from the weather, from the price tariff, from many other factors that are either public to them and private to them from the historical information. So the DSO system operator has an intelligent agent, the EVSE aggregator, the owners of the charging stations, they have an aggregator that works with the DSO, and the demand response aggregators also work with the DSO. So in this bilateral kind of market, we have the DSO that based on the needs, based on the optimal power flow, will send some signals of requests through the blockchain to the demand response aggregator and the EVSE aggregator, and then through the process that I'm going to show you, they're going to close the transaction through the blockchain. So one of the advanced electricity system operators in North America is IESO in Ontario, Canada, and they already have some rules for bilateral transactive energy market between the system operator and the aggregators. And for example, in those rules, basically we found that the DSO, the system operator, for example, Electra or Hydro Ottawa, can submit their offers to these EVSE charging stations at least 34 hours before the actual time that they need the energy. The aggregators, whether it's the demand response or the EVSE owner, should basically reply by counter offer, accept or reject or deny to the DSO at least 24 hours before the actual time of need by the system operator. After settling the contract with the DSO, for example, the EVSE aggregator should send the offers to the EV owners, EV car owners in that neighborhood or jurisdiction or control area for having the contract with them for the time that there is a need for V2G, vehicle to grid service. And that should be, the EVs should respond to that with a reject or accept at least 1 hour before the time of the need. And these are the rules coming from the IESO for this type of vehicle to grid and demand response transactive energy market. So, and these are some of the contract rules that we have logically formulated and put it into the smart contract. For example, the aggregators over generation. If they provide more energy than needed by the DSO, then the DSO will buy it at a reduced price. If the aggregator cannot provide the committed generation, so these are all the things that the smart contract is checking inside and monitoring by the meters and the point of injection. And so there are conditions and there are actions that the agent, the soft agent, which is the smart contract, will take, and will notify everybody in the peer, including the DSO, the aggregators for EVSEs, and the flexible loads. So if they cannot provide generation or they cancel the contract, then the aggregator should pay that DSO the cost of the damages. The DSO can cancel its offer at least 2 hours before the actual time of dispatching. And if the DSO cancels the offer less than 2 hours, then there should be, the DSO should pay aggregator the cost of the damages. So on and so forth. So I don't want to bore you with these kind of rules, but these are the rules that basically we understand. We read the documents, the white papers, the technical reports from each individual ISO in North America that we work with, and then we create these logics based on the contract rules, and then we formulate them into the smart contract. And this is one example that for this network that we have the DSO, we have the aggregator for demand response, we have the aggregator for EVSE or charging stations, and then those logical rules are in place in the smart contract, and the smart contract is distributed in the network and monitoring on behalf of each party. And so the results that we got for example, transactive energy market optimization for October 21st, 2019 at 12 p.m. is showing that, okay, so these car owners, Jonathan, Allison, Nicholas, Savannah, Lily, Sarah, Jacob, Victoria, and Tony, they have either charged their cars or discharged their cars, sold the power to the EVSE at different initial SOC levels and the final SOC levels that you can see in the table, and with the given battery capacities, and each individual transaction value that if it's negative, it means it was consuming charging. If it's positive, it means it was selling power, injecting power to the grid, and it was discharging. And the net transactive, basically transactive energy value at the end, the cumulative for all these drivers to the grid was about 57 kilowatt hour at 12 p.m. to help the grid. And in the green table, we can see that we have the PV sources, demand response, and these charging stations, whether AC or DC, and how much they consumed or injected to the grid. So this is a summary of the results. And these two basically graphs are clearly showing the effect of basically when you utilize DERs, including solar power, demand response, and EV cars for basically injecting power to the grid at the time of need through this transactive energy platform that we developed. You can clearly see the effect of those clean energy resources within the distribution power network in terms of GHG reduction. For this case, 1.6 ton of reduction. Loss cost reduction, going from about $30 dollar for the cost of energy for the loss that the end customers are paying in their bills for the wire charges. So we have reduced it to $2.57. So this is amazing. This is a lot of improvement in grid efficiency and reducing the losses and reducing that part of the bill for the end users. And so we have also increased the marginal basically stability margin of the voltages. So we can see that the voltages have been approved. The margins from basically they are at the 1 level and between 1 and 103 as opposed to the 0.97. So we have also improved the stability of the network in terms of voltage control. And the other graph on the right-hand side is showing specifically the value of V2G functionality, vehicle to grid. So the left-hand side is generally speaking about the combination of PV demand response EV. The one on the right side is specifically showing the value of vehicle to grid injection for this example, that you can see clearly that the V2G, when we have so many millions of cars, EV cars that are going and they're parking at Target store, shopping centers, and the owners, either the owners or the staff are spending a few hours in that shopping center, then they can basically make money from basically dispatching power to the grid and helping the grid. So it's a win-win situation for everybody. And so at the end, we want to show you the performance of our blockchain, which is pretty good. So the communication and computation time between the application and the server and the basically prosumers and the DSO, we can see here that the maximum communication computation time is for DSO offered to the demand response aggregator, which is less than one second. So all the times are less than 1 second in terms of communication and computation. And then if we scale this network with I don't know, 15, 20 of 100 EV cars and 1 DSO and about 12 distributed solar battery wind power to 10 times the size of this, then, and we consider a linear projection, then you're talking about less than 10 seconds of computation for all these optimization and blockchain-based transaction, which is pretty good. 10 seconds for a network of 10 times the size of the network that I just presented to you. And in my last slide, I want to show that we have partners such as IBM. We have used IBM blockchain and Watson together with other type of clouds that Sienna is one of our partners. And we have both in Canada and US partners, including Stantec, Luminex, Team E, SNC Electric, BluWave-ai, 2Click, Sunverge, and Project International. And academic-wise, we are working with Ryerson University, University of Toronto, University of Ottawa very closely, and Ontario Center of Excellence. Thank you for your time and patience. I'm happy to answer your questions. I appreciate your time. And,
okay, thank you, Ashkan. Thanks for your presentation. I think we can probably dedicate time to a few questions, given that we are over time. So please go ahead, unmute yourself, and ask your questions from each one of the panelists. Okay. I think people are the ones on the British time are looking forward to join their Friday night. Anyway, I can go ahead and ask a question from all the panelists to share their opinion about a topic that I briefly touched on the impact of COVID situation on the general business of smart grids, which microgrid is an element of. I will please go ahead and I briefly touched it in one of my slides, so I'm not gonna go through it and share my opinion in appreciation of time. But I'm curious to know each one of your perspective on the impact of COVID and what we are expecting post-COVID situation.
Oh, okay. I kind of agree with your perspective and vision that so the COVID changed our lifestyles and the way we consume energy. You know, but basically COVID has shifted the load, you know, from I don't know, offices to homes. So there is a shift between sectors because of COVID-19. And also in traffic, you know, the cars and the traffics, and so that's also affecting energy usage in another way, transportation. Overall, I think we are still dealing with the problem of you know, greenhouse gases, and we need to continue on you know, using utilizing more of these clean energy resources and developing software for handling and managing and monitoring those resources, because as we have seen, the COVID has shifted the loads and has affected the transportation, but still people are putting gas into their cars, and people, they need to you know, use natural gas to basically, you know, especially in Canada with the harsh winters, to warm up their houses. So the best solution and strategy is to basically keep working on strategies to utilize more and more of these clean energy, solar, battery, wind, and hydro, and at the same time developing software basically for monitoring and controlling these clean energy resources. So this is my view, basically. Thank you.
Thank you, Ashkan. Ehsan and Cameron.
Yeah. Sure. Yeah, I think this is a kind of the area that I believe that is that we can see from a different perspective. Actually, so it was interesting first to see what would be the impact of our overall load, because as you know, the people after COVID, so they would transfer more the stuff from working at the office to home, and at the actual, and my understanding was we are going to have more energy consumption at the cloud, but actually from our internal, we didn't see that much difference before and after COVID, because of some other certain element could affect. But in general, I think, as you said, this is a kind of the starting point to look at the operation of the energy resources and look at from the sustainability, because that can be a starting point, especially from the transportation perspective, because one side we may lose, we may have less CO2 emission because of transportation, but on the other side we may increase some of the energy from the other side. My feeling is that this can be a starting point for all the industry to look at and just move toward to have a cleaner grid and system and work toward that. But as you know, it impacted all economy, and it impacted all the different sector across the different industry. And that is not industry saying that, okay, that is going to affect better or worse. Still, that is questionable how we can react to that kind of effect in a positive way.
Great, thanks for your insight, Ehsan, and it's interesting to know that much has not been observed for in respect of your consumption at Microsoft, seeing before and after. That's an interesting insight. Cameron?
Yeah, I suppose my perspective is slightly different. I alluded in my presentation to the fact that during COVID, the electricity grid operators in the UK have dabbled with getting smaller generators to be flexible. And I think that if that is a sign of things to come in the future, which I think it is in the UK, then that will certainly be advantageous to sites that have the kind of AI capability built in. I guess for the particular industrial user that we are supplying at our project, they're dealing with municipal waste, and as far as I know, the waste streams, you know, they may be majored more on toiletry waste in the opening part of the pandemic, but you know, on a serious note, I think waste is waste. So the only way that that is likely to reduce is by us becoming more efficient at using less packaging and things like that, which I think is independent really of the COVID crisis.
Okay, thank you, Cameron. I appreciate it. So, okay, if there is any last-minute question from the participants, please unmute yourself. Otherwise, I would like to thank you again, everyone, our panelists, Daniel, and all the participants for your presence at this panel. I apologize if we went not a little bit, actually a little bit more than a little bit over time. Special thanks to those whose time zone has been a little bit tricky with this overtime situation in UK and in Asia. We in Canada are just entering our lunch break, and also on the eastern coast of US Canada. On the western coast, we are just entering around 9 a.m. I believe. Yeah. Anyway, Daniel, if you have any final comments, please go ahead. Again, I would like to thank you, everyone, for your participation.
Yes, thank you very much, Mustafa and Cameron and Ehsan and Ashkan. It was a great panel, very interesting topic, and very timely, and I'm going to be relevant. I want to thank everybody for attending this year. That will the conference for this year. Thanks for your patience in doing it online. I know these are unusual circumstances, but I appreciate all the participation, presentations, and Q&A. Publishing a website shortly that has links to all the recorded presentations, so you can watch anything in recorded format that you weren't able to attend in person. Additionally, PDFs of these presentations will be available through the same website, and as well as the attendee list. So the next edition of this forum will be next April in Bangkok. You can make it there. We were going to do it this year in Bangkok, but that was canceled due to the virus. But I'm confident that this by April of next year, things will be back to normal. So that's the plan. And if you have questions, if you would like to be a speaker in the next edition of the conference, I have you. And otherwise, thanks again for attending, and have a good rest of your day. Take care.
Thank you. Thanks. Bye-bye.
Thanks, everybody.
Thank you very much. Thank you, everyone.
Have a great day. Bye.
Thank you. Bye.